Somewhere in northern Europe, around 8,200 years ago, there was a night, or maybe a morning, we can't know exactly, when the sea simply didn't stop. It came in, the way it always had, and then it kept coming. And when it finally settled, a landscape that people had walked across for thousands of years was gone. Not flooded, not damaged, gone. Beneath hundreds of feet of cold, gray water, permanently, one wave, one event. And the map of northern Europe looked fundamentally different afterward. Here's what makes this story so quietly astonishing. The land that disappeared wasn't empty wilderness. It was home, forests, rivers, wetlands, animals, people. A whole inhabited world that we've only recently started to rediscover piece by piece, buried under what we now call the North Sea. And the wave that helped erase it wasn't a storm or a tide. It was something far larger and far stranger, born not on the surface of the ocean, but beneath it, hundreds of miles away, in total darkness, on a crumbling underwater slope off the coast of Norway. The event is called the Storegga Slide. The land it helped swallow is called Doggerland, and together they form one of the most dramatic, most quietly tragic chapters in the entire prehistory of the British Isles. Now, this isn't going to be a fast story. If you're here because you need something to carry you slowly towards sleep, that's exactly what this is built for. So go ahead and get comfortable. Let the details come at whatever pace they want to. We're going to move through coastlines and ancient landscapes, through the science of how continents are slowly reshaped, and how sometimes they're suddenly reshaped, and through the lives of the people who were actually there when the water rose and didn't fall back. But before we go anywhere, I want you to try something. Think about a place you know well, a road you drive, a park you walk through, a town center. Now imagine standing in that same spot, but the year is 8,200 BCE. Odds are, if you're somewhere in lowland Britain, the Netherlands, Denmark, or northern Germany, that spot wasn't coastline. It wasn't even near the sea. It was the middle of a broad, low-lying plain, a landscape of rivers and marshes and grazing animals and people living quietly, complicated, surprisingly rich lives. The English Channel was narrower. The North Sea was mostly land. Britain wasn't an island yet, not fully, not in the way it is today. It was a peninsula, still attached, still connected. What you now think of as the seafloor between England and the continent was once ground that someone walked on, that someone probably had a fire, a family, a sense of home, and then, eventually, the sea took it. The central question this whole journey is going to circle around is deceptively simple. How much did one wave actually matter? Could a single tsunami really help create island Britain? Or was this a longer, slower story that the wave just punctuated in one terrible night? The honest answer is both, probably, and the details are fascinating, so we'll get there. But for now, I'm genuinely curious where you are while you're listening to this. Leave a comment if you feel like it. What time is it where you are? Are you somewhere that might once have been Doggerland, maybe somewhere in England or Denmark or the Netherlands, lying in the dark above what used to be dry land? Because that's the thing about this story. For a lot of people listening, it's not ancient history happening somewhere else. It's the history of the ground beneath your feet. To understand what was lost, you have to go back a little further than the wave, not 8,200 years, further, to the ice. Because the story of Doggerland doesn't begin with a tsunami. It begins with glaciers, and with what happens to a landscape when they melt. At the peak of the last ice age, roughly 20,000 years ago, so much of the world's water was locked up in ice sheets that global sea levels were somewhere between 100 and 120 meters lower than they are today. Think about what that actually means. The continental shelves of northern Europe, those broad, shallow, gently sloping edges of the landmass, weren't underwater. They were land, exposed, cold, wind-scoured, but land. Britain wasn't just connected to continental Europe. It was deeply, geographically part of it. The same unbroken plain stretching from what is now the English Midlands, all the way to Scandinavia, interrupted only by rivers. Then the ice started to melt. Slowly at first, then with gathering momentum, the glaciers that had buried northern Europe began retreating northward. And as they did, all that locked water went somewhere, into the oceans. Year by year, century by century, sea levels rose, not dramatically from one generation to the next, but persistently, steadily. The kind of change that lives outside of human memory, because it moves slower than a single lifetime. By around 10,000 years ago, the flooding had already reshaped enormous amounts of coastline. The broad, flat plain connecting Britain to the continent was shrinking. Not disappearing, not yet, but narrowing. The southern North Sea basin was gradually filling. River valleys that had once drained across the open plain were becoming estuaries, then inlets, then bays. What had been the interior of a continent was becoming, incrementally, a coast. This is the landscape that became Doggerland, and it's worth pausing here to actually picture it. Doggerland wasn't dramatic terrain. It wasn't cliffs or peaks or anything you'd put on a postcard. It was low, genuinely low, much of it barely above sea level, even before the flooding accelerated, which meant it was rich in exactly the kinds of environments that are most productive for hunter-gatherers. River floodplains, reed beds, shallow lakes full of fish and waterfowl, broad marshes thick with plant foods, seasonal wetlands that would have drawn enormous herds of animals, woodlands of birch and hazel, and later oak gradually spreading northward as the climate warmed. And threading through all of it, large rivers, some of which we can still partially identify through seabed mapping. A major river system running roughly where the central North Sea sits today, fed by tributaries that included the Proto-Thames and what would eventually become the Rhine. We know this not because anyone wrote it down, but because the seabed remembers. Marine geologists surveying the floor of the North Sea have found the traces of river channels, meanders, oxbow lakes, the kinds of sediment formations that only happen in freshwater environments. Fishermen dragging nets across the Dogger Bank have pulled up the bones of mammoths, aurochs, and brown bears, pieces of peat, fragments of ancient wood. In a few remarkable cases, the harpoon points of Mesolithic hunters. Submerged forests have been identified along the coastlines of Britain, Denmark, and the Netherlands. Tree stumps still rooted in the peat, preserved under the shallow sea, some of them dating to the period when Doggerland was at its fullest extent. This is what geology does that no document can. It holds the shape of a world that no one alive remembers. The people living in this landscape were Mesolithic hunter-gatherers, and they were not by any measure primitive. This is a point worth making carefully. They had been living in and adapting to changing northern European environments for thousands of years. They understood their landscape with the kind of granular, intimate knowledge that comes from complete dependence on it. They knew which rivers flooded in spring. They knew where the elk wintered. They knew which mudflats would give up shellfish and which stretches of coast were reliable for sea fishing. Their lives were mobile, seasonally structured, deeply practical. They moved through Doggerland and its fringes the way skilled people have always moved through rich, complicated environments, following resources, returning to favored sites, maintaining what were probably well-established routes and territories across the plain. And here's the thing. The sea level rise they were already living through would have been visible to them, in a slow way. Not year to year, probably, but generation to generation. A headland that a grandfather described as now an island. A ford that was once reliable is now thigh-deep in salt water. Camps that had been used for centuries are abandoned as the coast creeps inland. This wasn't new. This had been happening for as long as anyone could remember, which is to say for all of human memory in this region. So there's a strange tension already built into this landscape before the wave ever arrives. This was a world that people knew was changing. They had always adapted. The plain had been shrinking for thousands of years, and the people living on it had simply moved with the margins, adjusting, relocating, rebuilding the fabric of their lives wherever the land held firm. It must have felt, in some deep and practical sense, manageable. Rivers flooded. Coasts shifted. You moved. You found somewhere else. This was the rhythm of life in a landscape defined by water. What nobody could have anticipated, what no amount of experience with slow coastal change could have prepared anyone for, was a morning when the water didn't rise gradually, when it didn't shift the margin by a few meters over a decade, when instead, without warning, it came all at once. But before we get to that morning, we need to spend some time in Doggerland itself. So let's go there, not to the seabed, to the land itself as it was. Picture a morning in late spring, somewhere around 8,500 years ago. You're standing on a low ridge, maybe 15 or 20 meters above the surrounding plain, which puts you higher than most of the landscape for miles in every direction. To the east, a wide river moves slowly through a floodplain, still green and waterlogged from the winter. Willow and alder cluster along its banks. Farther out, you can see the glint of open water. a shallow lake, or a broad tidal estuary. It's hard to say which. To the west, woodland. Birch and hazel mostly, with some oak beginning to move in as the climate settles into something warmer than anything the previous dozen generations had experienced. The air smells of mud and pollen and something faintly marine, because the sea, though you cannot see it from here, is not far. This is Doggerland in its middle period. Not at its fullest ice age extent when the plains stretched enormous and wind-scoured and half-frozen. Not yet in its final, shrinking, waterlogged state. This is Doggerland when it was still productive, still navigable, still a place you would choose to live if you knew the landscape well enough to read it. Which the people living there absolutely did. We don't know what they called this place. We don't know what language they spoke, or how they divided up the land between groups, or whether they had names for the particular rivers and ridges we can now only trace through seabed sediment. What we do know comes from objects, not documents. Objects. Fishermen working the southern and central North Sea have been accidentally dredging up evidence of Doggerland for well over a century. Mammoth teeth, bones of aurochs, the enormous wild cattle that no longer exist anywhere, brown bear bones, reindeer, woolly rhinoceros, species that place some of these finds deep in the Ice Age but others in the warmer Mesolithic period that followed, pieces of peat, ancient compressed plant matter that only forms in freshwater or very low salinity environments, fragments of worked wood, and in a small number of cases actual human artifacts, a barbed antler harpoon point, dredged up with a fish catch and recognized for what it was. Flint tools, a piece of human skull dating to the Mesolithic. Each of these objects is on its own a minor miracle of preservation. Together they form the outline of something real, a world that existed and then, in geological terms, vanished almost overnight. The scientific work of actually reconstructing that world relies on more than lucky fishing nets. Over the past 2 decades, archaeologists and geologists have used high-resolution bathymetric data, essentially sonar mapping of the seabed, to read the drowned landscape the way you would read a topographic map. What they've found are river channels. Not vague impressions, but actual preserved meanders, the looping, curving signatures of rivers moving slowly across flat ground. Oxbow lakes, peat deposits in sheltered hollows, ancient coastlines at different depths, each one representing a different moment in the slow flooding. By taking sediment cores from the seabed and dating the organic material within them, researchers can identify when specific areas transitioned from freshwater to brackish to fully marine environments. They can date the death of a landscape, layer by layer, and what those layers show is a place that was already shrinking long before the tsunami. This is the part that tends to get underplayed in dramatic retellings of the Doggerland story. The wave was catastrophic, yes, but the land had been retreating for millennia. The coast that people were standing on in 6,200 BCE was not the coast their great-great-grandparents had known. It was miles inland from it. Marshes were expanding where dry ground had been. Salt water was pushing into river mouths, killing the freshwater vegetation and replacing it with something different. Coastal dunes were shifting and sometimes breaching. For the people living through this, adaptation was constant. And that's the thing about genuine adaptation. It's often invisible from the inside. You don't experience it as a crisis response. You experience it as just how things are done now. Camps that had been reliable for generations would have been abandoned as the water table rose, and the ground became too wet to sleep uncomfortably. Communities would have shifted their routes. What had been an easy overland crossing between 2 good fishing areas might become a wade, then a short paddle, then too deep to cross at all. Diets would have shifted with the landscape. The deep riverplain hunting that was productive when the land was dry and firm becomes harder as the terrain grows wetter and more fragmented. But the wetlands themselves are generous in their own way. More waterfowl, more fish, more shellfish along the expanding estuary margins, more plant foods in the reed beds. You don't starve, you adjust. What we cannot say with confidence is exactly how any particular community organized that adjustment, whether there were territories that were fought over as they shrank, whether some groups moved willingly and others were pushed, whether the people living on the higher ground of what is now the Dogger Bank, a broad, shallow rise in the central North Sea that would have been one of the last areas to flood, thought of themselves as different from the communities on the lower plains. We're working with physical evidence and inference. The social texture of Doggerland life is almost entirely beyond recovery. What we can say, is that these were not passive people watching helplessly as their world diminished. Every piece of evidence we have from Mesolithic Northern Europe points to communities that were skilled, flexible, and extremely good at reading environmental change and responding to it. The coastal retreat was real. The adaptation to it was also real. The question is, what happens when adaptation has limits? When the change is no longer slow enough to absorb? That question was about to get an answer. To find that limit, we have to leave the low plains and go to the edge of another world entirely. North and east of Doggerland, beyond the marshes and sandbanks and the gently sloping continental shelf, the seabed drops away. Not a cliff, exactly, but a long descending shoulder of the Earth's crust, falling from shallow, sunlit waters into the dim cold of the deep Norwegian Sea. On that submerged slope, about 100 kilometers off the coast of what is now central Norway, something vast had been quietly assembling itself for thousands of years. Geologists call it the Storegga Slide. Storegga just means the great edge in Norwegian, and that's exactly what it is. The scar left by one of the largest submarine landslides we know about anywhere on Earth. If you could drain the ocean for a moment and stand out there on the edge, you would see a landscape that looks strangely familiar and utterly alien at the same time. Great step terraces where huge masses of sediment tore loose and slid downslope. Headwalls tens of meters high, where the seafloor simply isn't there anymore because it moved hundreds of kilometers out into the deep. Lobes and ridges of frozen motion, like a mountain of mud and sand caught mid-avalanche. All of that used to be part of the continental margin. Then, one day, it wasn't. To understand how something like that can happen, it helps to think about what had been going on in the North Atlantic for the 10,000 years or so before the slide. At the peak of the last ice age, enormous ice sheets covered Scandinavia, Scotland, much of the North Sea basin itself. A kilometer, sometimes more, of ice pressing down on the crust, grinding rock to powder, filling valleys with glaciers that slowly bulldozed their way toward the sea. All that rock had to go somewhere. As the ice flowed, it carved out material and carried it. When the glaciers reached the coastline and carved into the ocean, the meltwater plumes pouring out from under them dumped staggering amounts of sediment at the continental shelf edge. Sand, silt, clay, ground-up rock flour, year after year, century after century, all quietly piling up at the break between shallow shelf and deep basin. Think of sand being poured at the edge of a table. As long as the slope is gentle, it will just accumulate. But if the slope steepens, the pile gets taller and taller until it reaches a point where the grains can no longer support each other. Add one more grain, disturb the pile just slightly, and suddenly everything gives way in one rushing, sliding mass. The Storegga margin was that pile on the edge of the table. For thousands of years, glacial meltwater and post-glacial rivers had been loading it with fresh sediment, layer upon layer, water-saturated muds, unconsolidated sands. Material strong enough to sit there when undisturbed, but weak when pushed past their natural angle of stability. Underwater, gravity still works. Slopes can still fail. But the physics is a little different. Sediments can be partly supported by pore water, the tiny spaces between grains filled with fluid. If that pore water becomes overpressured, if there's too much of it or it can't escape, the sediment loses strength. It can behave not like a solid stack of grains, but like a very dense, very heavy liquid. Several things may have been nudging the Storegga sediments toward that unstable state. One is simple weight. Rapid sedimentation, after the Ice Age ended, meant new material was being dumped on top of older, water-rich layers faster than the water could escape. That traps pore fluids, increases pressure, and makes the whole pile more prone to collapse. Another possible factor lies frozen in the seabed itself. Gas hydrates. These are crystalline solids where methane gas is trapped inside cages of water molecules, stable at low temperatures and high pressures. They sit in a kind of delicate balance. Warm things up just a little, or drop the pressure slightly, and the hydrates can break down, releasing free gas into the sediments. The gas can raise pore pressures further, weaken the structure, and effectively lubricate potential slip surfaces. In high-latitude continental margins during the transition out of an ice age, conditions for gas hydrate formation and breakdown are perfect. Ocean temperatures are slowly changing. Sea levels are adjusting. The precise stability fields of those frozen gas deposits are being nudged. And then there is the crust itself, still responding to the vanished ice. When the Scandinavian ice sheet melted back, The removal of that kilometer-thick weight allowed the underlying rock to rebound. Not instantaneously, but gradually, over thousands of years. The land rises, the crust flexes. Offshore, that flexing can change stress patterns in the sediments and the rocks beneath them. Post-glacial rebound is not dramatic on human timescales. You'd never notice a shoreline creeping up a few millimeters per year, but over centuries it can load faults, alter the tilt of entire shelf segments, and nudge already unstable slopes a little closer to failure. Put all of these together and you get a picture of a margin that, by around 8,200 years ago, was primed, oversteepened, overloaded, full of water-rich layers and possibly gas-charged horizons. A sleeping giant that didn't look like much from the surface. Just another expanse of gray, restless sea. What finally pushed it over the edge is still debated. One candidate is an earthquake. The North Atlantic and Norwegian Sea are not quiet tectonically. There are faults associated with the opening of the ocean basin, with post-glacial rebound, with old fracture zones in the crust. A moderate to large quake shaking an already unstable slope could be enough to make it fail. Just as a skier's shout can sometimes crack a fragile snowpack and send it thundering downhill, a brief pulse of ground motion could turn poised potential energy into motion. Another possibility is that gas hydrate dissociation reached some tipping point. As ocean bottom waters warmed in the early Holocene, the zone where hydrates were stable may have retreated deeper. If enough hydrate converted to free gas at once, the resulting pore pressure increase could have triggered a runaway failure along a weak layer. It could also have been a combination of things: slow changes in temperature, long-term rebound, progressive weakening along a buried horizon. Then, one day, some small disturbance, an earthquake, a minor slump upslope, a pressure wave from another event, crossed an invisible threshold. The sediments slipped. When they did, they moved in a way that is hard to picture at human scale. This was not a little slump at the edge of a harbor. Reconstruction suggests that the Storegga Slide involved thousands of cubic kilometers of material. Imagine a layer of mud, sand, and debris up to several hundred meters thick, extending for hundreds of kilometers along the margin, suddenly detaching and accelerating downslope at tens of meters per second. Not a solid block, but a contorting, flowing mass that entrained more material as it went. As that mass moved, it displaced the water above it. Push a hand quickly into a bathtub and you get a small wave. Push something the size of a small mountain range into the North Atlantic in a matter of minutes, and you get something else entirely. This is where it helps to separate two very different ways the ocean can change. The people of Doggerland were deeply familiar with sea level rise. They had lived with it for generations. Year by year, decade by decade, high tide crept a little further inland. Saltwater fingers reached a little farther up the estuaries. Campsites that had been safe on dry ground needed to be moved a few hundred meters, then a kilometer. The change was inexorable, but slow enough that you could adjust your life around it. Build your shelters a little higher, shift your hunting grounds. Teach your children that the place where your grandparents gathered shellfish is now part of the sea. A tsunami is the opposite of that. Sea level rise is measured in millimeters per year. A tsunami is measured in meters per minute. It is not the ocean slowly claiming land by long negotiation. It is the ocean taking it by force. The Storegga Slide was one of the mechanisms by which that force can be released. When a huge volume of sediment collapses suddenly on the seafloor, it acts like a giant paddle, shoving the water out of the way. That shove sends a pulse of energy through the ocean. At first, out in deep water, it doesn't look dramatic. Tsunami waves in the open ocean can be only a meter or less in height, with wavelengths of tens or even hundreds of kilometers. A ship passing over would barely feel a long, slow rise and fall. But the energy is there, moving outward in all directions from the source, across the Norwegian Sea to the north, toward the coast of Norway to the east, and crucially, southwest and south, toward the British Isles and the broad, shallow platform of the North Sea. As those waves travel, they transform. In deep water, they are fast and low. In shallower areas, where the seafloor rises under them, they slow down and grow taller, compressing their energy into less depth. They bend around underwater features, refract along slopes, interact with coastlines that can either focus or diffuse their power. By the time the Storegga tsunami reached the coasts of what is now Scotland and the narrowing, shoaling basin over Doggerland, it was no longer just an almost invisible bulge in the open ocean. It was a wall of water, or more precisely, a sequence of surges and withdrawals capable of ripping up peat, dragging trees and animals inland, and leaving behind distinctive layers of sand where no marine sand should naturally be. But for now, at the moment of the slide itself, none of that had happened yet. The people waking up on the river ridges and estuary banks of Doggerland would have had no sense that far to the north and east, the seafloor had given way. That a sleeping giant on the edge of Norway's underwater slopes had turned over in its sleep. All they would have known, when they knew anything at all, was the water. Rising, not over millennia, but over minutes. Rushing, not creeping. A wave, born in darkness, beginning its long, invisible journey across the North Atlantic and into the shrinking world they thought they understood. Far out over the dark water, the wave was already moving. Not one neat crest like you might picture when you hear the word wave, but a whole broad heave of the sea itself, a slow lifting and lowering of the surface that stretched for tens of kilometers from front to back. This is the first strange thing about tsunamis. They are not like wind waves, the small, choppy patterns you see running across the ocean on a breezy day. Those familiar waves have short wavelengths, maybe a few meters from crest to crest, and they live in the skin of the ocean, stirred up by air skimming over water. The tsunami is different. Its wavelength can be longer than entire counties. In deep water, from the top of one crest to the top of the next, can be the distance of a day's walk. That means the whole upper layer of the ocean is involved. The disturbance from the Storegga Slide didn't just ruffle the surface. It pushed a moving bulge and hollow through the entire water column, from surface to seafloor. Because the wavelength is so long and the ocean is so deep, a tsunami can travel incredibly fast. There's a simple relationship that oceanographers use. The deeper the water, the faster the wave. Out over the deep Norwegian Sea, where the bottom lies thousands of meters below, that Storegga pulse may have been racing along at hundreds of kilometers an hour. Not quite the speed of a jet, but more like a cruising airliner than any storm swell. Yet if you had been on a boat above it, you might not have noticed very much at all. No towering wall of foaming water, no sudden crash, just a gentle, eerie thickening of the sea. The surface would rise a little, stay high for a long time, then sink again. So slow that you might blame your senses, or a change in the weather, or the tide. The ocean carrying a hidden bruise under its skin. As that long bruise spread out from the slide scar, it began to encounter the complicated geography of the North Atlantic basin. The seafloor is not flat. Ridges and plateaus, channels and banks, all lie hidden beneath the surface. And just as wind shapes itself around hills and valleys in the air, tsunami energy is shaped by the underwater landscape. When a tsunami travels over very deep ocean, it has room to spread its energy through a tall column of water. As it runs up onto a continental shelf, into shallower depths, it suddenly has less room. The bottom rises to meet it. The wave has to slow down because the water is now shallower, but the energy it carries hasn't gone away. Slow a wave without losing its punch, and something has to give. The wavelength shortens, the water piles higher. That's the second strange thing about tsunamis. They grow not because more water is being added, but because the same disturbance is being squeezed into a shallower space. You can imagine it like pushing a carpet across a floor. On smooth wood, it can glide out, low and wide. Push that same carpet into a narrow hallway and it has to bunch up, rising in folds. The continental shelves around northern Europe acted like the edges of a giant hallway. On the Norwegian side, the shelf is relatively narrow and steep. The wave had less distance over which to slow and rise, but when it hit, it would have met high, rocky coasts and fjord mouths that could catch and reflect its power. To the southwest, toward Britain and the drowned plains of Doggerland, the shelf is broad and gently sloping. The North Sea basin is like a shallow ball set on the side of the deeper Atlantic. It shoals gradually from hundreds of meters to tens, and then to single digits as it approaches the old river valleys and lowlands. That shape matters. As the Storegga tsunami crossed the deep Norwegian Sea and approached this tilted bowl, its speed began to fall. From hundreds of kilometers an hour to something slower, but still unstoppable. The front of the wave started to feel the drag of the rising seafloor. The back was still racing in from the depths, piling into the shallowing water ahead. The wave steepened, but it didn't do so evenly. Wherever the seabed formed a natural ramp, the wave climbed higher. Wherever there were deeper channels, old glacial troughs, ancient riverbeds now flooded, the energy could run farther in, funneled like wind through a mountain pass. Coastlines complicate things further. A wide open beach allows the wave to spread its force over a long, flat surface, losing some of its height as it rushes inland. A narrow bay, a funnel-shaped estuary, a river mouth pointing straight toward the incoming surge can do the opposite. They concentrate the water, making it run higher and faster. Ancient Scotland and the coasts around the North Sea were full of such features. Long inlets carved by glaciers, drowned valleys, braided estuaries where rivers entered the low plains. Each one was a potential lens for tsunami energy, a place where the sea could rise not by a little, but by many meters. From above, if you could have watched with impossible detachment, you would have seen the wavefront bending as it moved onto the shelf. Parts of it refracted, turned toward shallower areas, like light bending when it passes from air into glass. Some energy wrapped around headlands and islands. Some raced up the deep central troughs of the basin, then spilled sideways over banks and shoals. Looking down, you'd see not one neat ring spreading out, but a constantly warping, splitting, merging pattern of long swells, all born from the same initial shove, all being sculpted by the shape of the seafloor and the line of the land. On the ground, none of that pattern would be visible. What people would see would depend very much on where they stood. Along some shores, the first sign might have been a strange, unnatural retreat of the sea. In many tsunamis, the first arrival at the coast is not the crest, but the trough, the low part of the wave. When that happens, the waterline can suddenly pull back, exposing seafloor that has never been dry in living memory. Rocks slick with algae, shellfish beds, the dark mouths of channels, fish flipping helplessly in the air. To people used to a slow, predictable tide, this kind of rapid drawdown would be shocking. The sea emptying itself in minutes instead of hours, rivers momentarily flowing downstream through yards of sudden extra space, boats stranded at crazy angles. Animals often notice such things first, birds on the mud flats taking off all at once, seals and dolphins moving in odd hurried patterns, away from shore instead of toward it. Herd animals lifting their heads, scenting something they don't understand. On other stretches of coast, especially those facing directly into the incoming crest, or lying inside funnel-shaped bays, there might be no warning retreat at all. Just an already rising tide surging higher, faster, as if some invisible hand had tipped the whole horizon toward the land. Sound would change too. Far offshore, a tsunami is nearly silent. As it shoals and breaks, it can become a roar, not like thunder exactly, but like an endless rushing wind filled with grinding and snapping noises, wood splintering, stones rubbing, trees tearing from the soil. Yet even close to shore, the first moments might feel weirdly quiet. People pausing at the edge of the water, puzzled by how fast the current is running, how odd the waves look, how the usual pattern of ripples and little breakers has given way to a single smooth rising sheet. Then the line between sea and land blurs. Tsunamis don't always arrive as sharp, glassy walls like in paintings. Often, especially on gently sloping coasts, they look more like a fast-moving tide that refuses to stop. Water pushing up the beach, over the dunes, across the low ground, higher than any remembered storm, carrying with it everything that isn't rooted deep or heavy enough to resist. Driftwood, peat, soil, animals, shelters, people. And the first surge is rarely the last. Because a tsunami is a whole train of long waves, not just a single crest. The sea can pulse in and out for hours, one surge higher than the last, another arriving from a slightly different angle after being reflected from a distant headland. Between them, the water may race back, turning rivers into torrents that suddenly flow seaward, dragging debris and bodies and uprooted trees. For the Mesolithic people around the North Sea, that would have meant chaos that refused to resolve. Climb a tree and survive the first rush, only to find the trunk scoured out around its roots by the retreat, ready to topple when the next wave comes. Take refuge on a low hill, watch the water slow at your feet, and then realize that what you thought was the end is only a pause before the next higher surge. Yet it would not have been the same everywhere. Some stretches of the ancient coastline might have seen only a few meters of unusual flooding, enough to swamp a camp, drown a hunting party, rearrange a riverbank, but survivable if you were far enough inland or lucky in your choice of ground. Other places where the wave was focused by bays and channels, or where low plains lay close to the shore, would have experienced something far worse. Water climbing as high as the tops of trees, racing inland for kilometers, erasing whole tracts of land from practical use in a single violent hour. This patchiness is something geologists see today when they map the thin sheets of sand the Storegga tsunami left behind. In some cores, the tsunami layer is thick, coarse, full of ripped-up peat and broken shells, evidence of powerful, turbulent flow. Just a short distance away, the same horizon is a faint smear, a few grains thick or missing entirely. The wave's touch was uneven. For the people living around the North Sea basin, that meant fate was uneven too. A family camped on a higher bluff might have watched the strange withdrawal and return of the sea from a terrifying but safe distance. Their stories later describing a river that turned around and tried to climb back into the sky. Another group, settled on a low, fertile spit between channels, might have had no such margin. For them, there was only the rushing water, and then nothing at all. And then there were the places most exposed of all. The outer islands and headlands of what is now northern Britain, standing like stone teeth on the edge of the North Atlantic, and the flat, river-crossed plain of Doggerland itself, lying directly in the path of the shoaling wave inside the North Sea Bowl. As the tsunami train moved farther onto the shelf and curled into the narrowing basin, those areas were waiting, though they did not know it, for the full expression of the wave's transformed power. The next part of the story belongs to them, to the cliffs and bays of ancient Scotland, and to the broad, low country that would soon learn what it meant to have the sea arrive not as a neighbor, but as a sudden, devouring guest. On the far northwestern edge of Europe, the first stone to meet the wave was Scotland. Not the Scotland you know today, with its mapped coastlines and named islands, but a more intricate version. Sea level was lower than now, the shoreline bit deeper into the land. Long, glacially carved inlets reached far inland, their steep sides remembering the ice that had once filled them. Low plains and peat-filled hollows fringed the mouths of rivers. Offshore, smaller islands and skerries, some now drowned, some still here, stood as scattered stepping stones between the deep Atlantic and the shallower shelf. Into this maze came the Storegga tsunami. As the leading swell struck the outer headlands, it began to fold itself around the contours of the coast. Swell lines that had been almost straight in deep water now kinked and curved. One part of the wave rushed into a fjord-like sea lock, another wrapped around an island, another rode up over a broad, gently shelving bay. The same pulse of displaced water, constantly reshaped by the land. In narrow inlets cut by ancient ice, the effect would have been dramatic. Take a long sea lock, something like modern Loch Broom or Loch Torridon, but with its shoreline slightly farther out, its head perhaps lined with mixed woodland and peat bog. The mouth opens to the Atlantic. Behind it, the loch narrows and bends, a deep groove incised into the highland rock. When the tsunami pushed into such a feature, the water couldn't spread sideways. It was forced to run inland, its energy squeezed between the walls of the glen. The wavefront climbed the loch like water racing up a tilted gutter, slowing as it went but growing steeper, higher, piling against the head of the inlet. Geologists have tried to read the traces of that inland rush. Around the Moray Firth, along the east coast of Scotland, and in low-lying pockets on the west, they have bored into ancient peat and mud, drawing up long, dark cores that are like rolled-up scrolls of landscape history. Layer by layer, century by century, the quiet work of rivers, tides, and plants has been laid down in thin sheets of silt and decomposed vegetation. Most of those layers are what you would expect from gentle, everyday processes. Fine peat from centuries of moss and heather growing and dying on waterlogged ground. Thin laminations of estuary mud, built grain by grain as tides creep in and out. Pollen grains, fragments of insect wings, bits of charcoal from distant campfires or natural fires. Then, at the level corresponding to about 8,200 years ago, something different appears. A band of sand, sometimes only a few centimeters thick, sometimes much more. Clean, sharp-edged grains lying where no normal storm should have put them. Sand abruptly inserted into the quiet sequence of peat and silt. In places, that sand is coarse, full of broken shells and ripped-up clumps of older peat, rolled and tumbled together by violent water. In others, it's finer, a more subtle smear, hinting at a weaker incursion. Above and below, the peat continues, as if a peaceful bog had, for a brief moment, been overwhelmed by the sea and then resumed its slow, steady growth. These tsunami deposits, as geologists call them, are some of the clearest evidence that the Storegga wave reached Scotland and the Northern Isles. They're not everywhere. That patchiness, the same uneven touch hinted at earlier, is written in the cores. Drill in one hollow, and you hit a thick sand layer, obvious and disruptive. Drill a short distance away, and the horizon is faint, or missing altogether. Even in the places hit hardest, the wave did not leave a single uniform signature, but in enough locations, along parts of the Moray Firth, in the lowlands round Montrose, across stretches of the Shetland and Orkney coasts, the same story repeats. Peat, then sand out of place, then peat again. Dating these layers is a delicate exercise. Peat is full of once-living material, leaves, stems, bits of wood. Each piece contains carbon that was taken from the air while the plant was alive. Over time, the radioactive isotope carbon-14 in that material decays at a predictable rate. By measuring how much remains, scientists can estimate how long it has been since that plant stopped exchanging carbon with the atmosphere, how long since it died and became part of the peat. In practice, they don't date the sand itself. Sand is just mineral grains, it doesn't carry a clock. Instead, they date the organic material immediately below and above the tsunami layer. A twig buried in peat just under the sand. A fragile leaf preserved in the peat that grew back on top. Those two ages. Not earlier than this, not later than that. Bracket the time when the sand was laid down. Even here, there are uncertainties. Radiocarbon dating needs calibration, because the amount of carbon-14 in the atmosphere has varied over time. Peat can mix old and new material as roots grow downward and animals burrow. A twig might already have been decades old when it fell into the bog. Each source of uncertainty widens the window a little. So when scientists say the Storegga tsunami deposits in Scotland date to about 8,200 years ago, they are speaking in rounded terms. The exact year is blurred, but the cluster of dates, the consistent stratigraphy, and the match with similar sand layers in Norway and around the North Sea build a converging picture. A single, large marine incursion event, region-wide in extent. The thickness and elevation of those sand sheets give another kind of information. Hints about how high the water must have reached. Around the Montrose Basin on the east coast, tsunami sand has been found several kilometers inland, and at elevations that suggest water climbing multiple meters above the normal high tide of the time. In some Scottish sites, researchers have argued for run-up heights, how high the water reaches on land of perhaps 10, 15, even more meters above the pre-existing shoreline. But these reconstructions come with careful caveats. Land has not been still since that day. Northern Scotland, relieved of the weight of the last Ice Age glaciers, has been slowly rising. Other parts, weighed down differently, have been sinking. Shorelines have migrated as sea level climbed with the melting of continental ice. To estimate how high the tsunami ran, scientists must reconstruct not only the wave, but the ancient ground it crossed, correcting for uplift and subsidence, for changing tides, for the gradual drowning of the lowlands. Computer models of tsunami behavior in reconstructed ancient basins suggest impressive heights in some fjords and embayments, but the exact numbers vary with each assumption. Change the roughness of the land surface, adjust the water depth slightly, and the simulated run-up shifts. This is why responsible researchers talk in ranges, in best estimates, in phrases like possibly up to, rather than precise, confident figures. What is clear, even within those uncertainties, is that in certain parts of Scotland and the Northern Isles, the sea rose far beyond any ordinary storm surge. Imagine following the wave's path along the coast. On the exposed Atlantic side of the Northern Isles, the Orkneys and Shetlands, the first impact would have been blunt and direct. High cliffs, broken by narrow geos and coves, facing straight into the incoming swell, water smashing against rock, rebounding in chaotic interference patterns. Sea caves suddenly flooded to their roofs, spray leaping higher than usual, driven by a swell that did not behave like any winter storm. Where the islands offered low ground, broad, shallow bays or low saddles between higher ridges, the wave could pour across, turning peninsulas into temporary islands, turning flat grazing grounds and birch scrub hollows into seafloor. In some Shetland peat deposits, tsunami sands lie surprisingly high, above modern sea level, hinting at local amplification, the wave funneled and focused by tortured coastlines and submerged ridges. Farther south and east, in the shelter of the Moray Firth, the character of the inundation would have changed. Instead of crashing straight in from the open Atlantic, the wave energy arrived after being bent and guided along the shelf edge, wrapping around headlands, splitting and merging as it met the narrowing gulf between the highlands and the lowlands. Here, low-lying plains and estuaries offered the wave room to run inland in broad sheets. River mouths would have been strange, dangerous places. Picture a tidal reach where fresh and salt water meet. Mud flats exposed and covered twice a day, birds feeding, people perhaps gathering shellfish or tending fish traps woven from wattle. When the tsunami arrived, the river's ordinary flow would have been instantly overwhelmed. For a few minutes or more, the current would reverse, not in the gentle, predictable way of a normal tide, but as a roaring, debris-filled surge racing upstream, climbing banks, curling into side channels. In deeper, fjord-like firths, the wave may have set up a standing oscillation, a seiche, sloshing back and forth as reflected crests met incoming ones. The water level rising and falling in great unnatural pulses for hours after the main surge, quietly continuing the work of erosion and rearrangement long after the first violence had faded. All of this we infer from sand and mud, from careful surveying of old shorelines, from models run on modern computers. When scientists lay out their conclusions, they are forced to be modest. The sand tells them there was marine flooding. The elevation and extent hint at minimum water heights. The dating ties the event to the time of the Storegga Slide. Beyond that, there is room for debate. Exactly how high, exactly how fast, exactly which hollows filled and which escaped. But beneath the technical discussion lies a simpler human question. Who was there to see it? Along the coasts of Mesolithic Scotland and the Northern Isles, people had already been living for thousands of years. Hunter-fisher-gatherers who knew the tides and seasons as intimately as others, no streets and clocks. They built shelters of wood, bone, and hide in sheltered bays. They moved with the fish runs and the seal haul-outs. They left behind middens of shells and bones, scatters of microliths, tiny stone tools used in composite weapons and implements. To them, the sea was not an abstraction. It was a path, a pantry, a boundary, a presence. When the Storegga wave reached these shores, it would have translated itself into their lives in countless specific ways. A camp drowned overnight, a canoe pulled ashore and then carried inland by water that should never have reached that far. A familiar sandbar, used for generations as a crossing place, suddenly gone, or shifted, or dangerous. We do not have their words for it. No carved record, no story written down at the time has survived. But the sand layers and the rearranged shorelines, the sudden break in quiet peat building, all whisper the same question forward through the millennia. What happened to the people along the low coasts, in the mouths of the firths, on the riverine plains? To follow that question to its most vulnerable ground, we have to turn away from the rocky promontories of Scotland and look out across the shallower bowl of the North Sea, toward the wide, drowned plain of Doggerland, lying directly in the path of the rising wave. The first thing to understand about Doggerland is that, by the time the Storegga tsunami traveled its way across the North Sea basin, this was already a landscape under pressure. For thousands of years after the last ice age peaked, sea level had been rising, not in sudden leaps, but in slow, persistent increments, a few millimeters a year, a shoreline stepping inland, season by season, generation by generation, so gradually that no single person would have seen it as anything except the way the world worked. On the broad, low plain that once connected Britain to the continent, this change didn't look like a wall of water swallowing the land. It looked like creeping marsh. What had been dry, grassy ground became seasonally waterlogged. Shallow depressions that once held only winter meltwater lingered into summer as ponds and pools. Channels braided and rebraided across the surface, seeking the easiest line toward the deepening sea. Forests retreated to slightly higher rises. In their place, reed beds and alder spread. Then more open wetlands. In some pockets, peat began to build. Plant material accumulating faster than it could rot, locking up ancient pollen and seeds in its slow, dark archive. Cartoon versions of Doggerland sometimes imagine a single, continuous field of dry grassland stretching from Yorkshire to Jutland. The reality, by 8,200 years ago, was more tangled and amphibious. There were still dry islands and ridges, higher ground that would have felt secure underfoot, places to camp, to butcher game, to store worked wood and stone. But between them ran shifting belts of mudflat, marsh, estuary, and shallow tidal lagoon. In some places, the sea already pushed in as winding inlets. In others, freshwater rivers wandered sluggishly across boggy ground before finally giving themselves up to brackish creeks. This is what made Doggerland so rich for Mesolithic people. A patchwork of habitats full of fish, waterfowl, shellfish, deer, and wild cattle, moving between woodland and open ground. But it also made it vulnerable. Low, flat countries are gentle while the water behaves. When the water stops behaving, there is nowhere to hide. As the Storegga wave crossed the deep Norwegian Sea, its energy was mostly hidden. A broad, low hump of water, perhaps barely noticeable in open water. But as it ran up onto the shallower shelf of the North Sea, it began to change character. In shallower depths, the lower part of the wave felt the seabed. Its speed dropped, its wavelength shortened, and the energy that had been spread invisibly through depth began to express itself in height. The swell steepened, separate wave fronts reflected from banks and ridges, interfering, amplifying, dulling in complex patterns. Oceanographers, using reconstructed bathymetry, estimates of what the seafloor looked like back then, run computer models of this passage. They watch simulated color bands of water height curl over submerged sandbanks, meet in the shallower bowl of the central North Sea, and surge onward like a slow, muscular breath of the ocean. When that surge met Doggerland's low margins, it did not politely stop at the ordinary shoreline. Imagine a tidal creek that usually fills and empties with the twice-daily pulse of the sea. Its banks are muddy, lined with reeds. On higher ground to either side, Mesolithic people have small camps, hearths ringed with stone, piles of worked flint, racks for drying fish or meat. On a normal high tide, the water might lap partway up the bank, wetting the roots of the reeds, nudging a little farther on stormy days. The people who live here know its moods. They know where to pitch their shelters to stay dry. Now imagine the difference between that and a tsunami. Instead of the familiar gradual rising and falling, the water begins to come in as a single, sustained push. The creek mouth widens, the surface level climbing and flattening at the same time. The current reverses and keeps on reversing, gaining speed, carrying silt, broken shells, maybe bits of distant shoreline. On level ground, a difference of only a few meters in water height is enough to carry the sea far inland. There are no cliffs to stop it, no high dunes or rocky steps. The land lies almost like a tabletop, tilted just slightly toward the sea. As the wave's front runs over the marsh, it spreads into a sheet. It does not need to be a towering wall to be dangerous. 1, 2, 3 meters of fast-moving water over an open plain will lift and carry almost anything not firmly rooted. Driftwood, stored belongings, fish traps, boats dragged up on the bank, the loose topsoil itself. Even if the highest crests were localized and variable, as models suggest, the general effect on low-lying stretches would have been the same. The sea, for a brief span, everywhere at once. Then comes the backwash. After the leading pulse passes as far inland as its energy will take it, gravity begins to pull it back. Water that has drowned the marsh and surged through woodlands now drains toward the lower roots, channels, swales, shallow depressions leading back to the main basins. That retreating water can be as transformative as the initial surge. It strips vegetation, scours out new runnels, widens existing creeks. It picks up sand and silt and broken shells from the transient shoreline it has created and redeposits them in quieter backwaters as it loses speed. The very mechanics that made peat so good at recording peace, layer upon fine layer of gentle accumulation, now let it act as paper for a single, sharp stroke of marine material. Somewhere in one of those depressions, perhaps in what was once a freshwater hollow, a few centimeters to a few tens of centimeters of sand are laid down over peat. Salt water has flooded a place that was used to rain, groundwater, and occasional river overflows. The plants that come back afterward have to deal with that sudden change, and for a while, or perhaps for good, the community shifts. Multiply that process by hundreds of channels and hollows across a vast plain. We do not yet have neat, continuous cores from the hull of Doggerland. Almost everything we know comes from the margins, from present-day coasts in eastern England, the Netherlands, Denmark, and from samples occasionally brought up during North Sea construction and dredging. Somewhere under the shipping lanes and fishing grounds, similar tsunami sand layers may sit, but they are hard to reach. This is one reason the precise impact on Doggerland is so difficult to reconstruct. Underwater, erosion and later sedimentation keep working. Tidal currents rake across the seabed, reshaping sandbanks, cutting and backfilling channels. In some places, later glacial and post-glacial deposits lie thick over older surfaces. In others, older layers are exposed but patchy, truncated by ancient river systems that have themselves been drowned. Coring at sea is more complicated and expensive than pushing an auger into a peat bog on land. Each sample is a narrow vertical glimpse, separated by long distances from its neighbors. When a core does show a suspiciously sharp band of sand in the right age range, scientists must decide, is this a tsunami deposit, a storm layer, or something else entirely? Again, they turn to models. By combining bathymetric reconstructions of the ancient North Sea with calculations of the Storegga Slide volume, they can simulate where the wave's energy would have focused, how far inland it could have reached, and which areas of Doggerland would have been most strongly inundated. They test different scenarios, slightly higher sea levels, slightly lower, different shorelines, variations in the exact shape of the slide. What emerges is not a single, crisp image, but a family of possibilities. In many of those, broad swathes of Doggerland's lowest ground, already marshy, already flirting with the sea, are overtopped. Islands of higher land remain as temporary refuges. Some ridges are cut off for a while, turned into short-lived islands by salt water filling the belts between. Certain river courses are rerouted, their mouths silted up or opened wider by the pulse. From a human point of view, the most immediate effect would have been on camps and the subtle infrastructure of daily life. Even if the main wave heights in the central basin were lower than at some Scottish fjord heads, the combination of flat topography and a high water pulse would have been unforgiving. Camps pitched on what had always been safe high banks might suddenly find themselves surrounded by water, the lower approach paths and foraging grounds submerged. Storage pits could be flooded and contaminated with salt, smoked fish washed away, caches of bone and antler carried off or buried under new sediment. Firewood and worked timber, so carefully gathered in an open landscape, might end up scattered or waterlogged beyond practical use. Freshwater sources would have been especially vulnerable. Shallow wells dug near camps, using the freshwater lens that often sits atop brackish groundwater, could turn salty for a time. Small ponds and cut-off meanders that served as reliable drinking places would have been tainted or physically altered. Even where people survived the water itself, they faced a changed hydrology. Places that were safe to drink from before might now carry the sting of the sea, and yet it is important to separate in our minds the suddenness of the tsunami from the longer drowning of Doggerland as a whole. The Storegga wave did not by itself erase the land bridge between Britain and the continent in a single night. That connection had been narrowing for centuries. The shallowest areas were destined to go under, tsunami or no tsunami, as global sea levels continued their slow climb in response to distant melting ice. Think of the tsunami instead as an accent, a sharp, disruptive event superimposed on a slow trend. For people living on the plain, the broader story was gradual, more frequent flooding of familiar spots, more land becoming wet underfoot, certain trails turning unreliable at particular tides. The tsunami was a sudden, confusing episode within that longer narrative. It may have locally hastened the abandonment of some low-lying zones. It may have made certain areas feel less secure, nudging groups to prefer higher ground that, in any case, would soon become islands. Archaeologically, that distinction matters. The ongoing submergence of Doggerland leaves a diffuse signature. Layers of estuarine and marine sediment over what used to be terrestrial soils, preserved tree stumps, peat layers now buried beneath sand and silt. The tsunami, if it left its mark at all in the central parts of the plain, will be just one particular sandband among many, only distinguishable by careful dating and context. And that, in turn, is why our picture of the drowning must remain modest, almost quiet. There is no single grand ruin on the seafloor, no line of toppled stone walls to point to as the moment it happened. Instead, there are scattered hints. A peat bed here with an unexpected marine layer, a submerged forest there with a strange disruption in its growth history, a model's colored contours suggesting a surge across a particular paleochannel. From these, we infer a lived experience of loss and adjustment. People whose grandparents had known a slightly larger land, whose parents told stories of hunting grounds now only reachable by boat, would have watched as the sea occasionally behaved in unnerving ways, creeping a little higher, flooding a little farther. The tsunami added to that, perhaps turning a marginal place into an untenable one, erasing a specific camp, destroying a particular crossing. In the generations that followed, the memory of a single great flood may have blended into the wider story of a land that was, year by year, becoming more sea than soil. By the time Doggerland itself stood as one of the last great islands in the center of the basin, and then finally slipped beneath the tides, the people whose ancestors had walked dry-foot from Britain to Europe were already living with a different geography. To see how they responded to that changing map, how Mesolithic lives folded themselves around advancing water, we have to move from the drowned plain to the survivors' shoreline and listen for traces of how they carried on after the wave. If you follow those survivors to the nearest dry edges, what would later become the eastern coast of Britain, the low shores of what is now the Netherlands and Denmark, you don't find cities or even villages in the way we usually imagine them. You find people moving. Mesolithic life around the North Sea was built on motion. Small bands, maybe 20 or 30 people, following what archaeologists call seasonal rounds. In winter, clustering in sheltered valleys or near reliable fresh water, burning through carefully hoarded firewood and stored fat. In spring and summer, fanning out along rivers, estuaries, and coasts, taking advantage of spawning runs, nesting birds, ripe berries, young deer. There were no permanent houses in the modern sense. There were favored places, clearings with good light and dry soil, river bends with easy landings, sandier patches on the coast that drained well after rain. People came back to those places again and again, building up quiet layers of debris, flakes of worked flint, broken bone, charcoal, until, thousands of years later, we find them as sites. Across the broader North Sea basin, these bands were not isolated in the way our map might suggest. They were linked by routes that ignored the later boundaries between land and sea. A river that today empties into the North Sea was once a road into the heart of Doggerland. A line of low hills that now form a chain of islands once continued as a single spine across a wider plain. Along those routes, there is evidence for long-distance movement of stone. Flint and other tool-making materials carried tens, sometimes hundreds, of kilometers from their original outcrops. That implies trade or exchange, gifts passing from group to group, obligations and friendships knit across distance. The tools themselves were small, precise, and standardized. Mesolithic craftspeople around the North Sea made microliths, tiny, carefully shaped stone pieces, often less than a few centimeters long, set into wooden or bone shafts with resin and sinew to form composite arrows, barbed points, knives. They made bone harpoons with regular repeating barbs, polished adzes and axes for working wood, and probably nets, traps, and baskets woven from plant fibers that almost never survive in the archaeological record. They used fire to clear patches of woodland, encourage browse for game, and maintain open edges where animals were easier to track and ambush. Into this mesh of people, tools, and landscapes, the Storegga wave arrived as a disruption, not an ending. On the day itself, reactions would have been very simple and very old. Run for higher ground, grab children, shout warnings down the bank, drag a boat if you can, abandon it if you cannot. The advantage of a mobile society is that almost everything important can, in principle, be moved. The disadvantage in a flat place is that water moves faster. In the immediate aftermath, the survivors' world would have felt uncanny. Familiar landmarks gone or altered, shorelines redrawn, freshwater sources brackish, trails leading to drowned crossings. A favorite low-lying camp replaced by a raw, scoured surface of sand and wreck. Bodies of people and animals tangled in debris at the new high tide line. What happens next is where we leave physics and enter plausibility. One response, almost unavoidable, would have been retreat to higher ground. Not everyone would have done it permanently. Some bands might have treated the wave as a terrible one-off event and, once things seemed calmer, drifted back toward the rich lowlands. But others, especially those who had lost many people or seen their most reliable territories transformed, may have shifted their home ranges inland along rivers into more wooded country, onto hills that offered a clearer sense of security. Over generations, those choices leave faint traces, clusters of sites edging slightly farther upslope, more activity on ridges overlooking former wetlands. Another response would have been regrouping. These were not solitary nuclear families. Kin networks radiated out from each band, and alliances mattered. A group that had lost members might seek out relatives they usually only visited in certain seasons, asking for help, food, or space to stay through a winter. A rich salmon river might suddenly support more people than before, its banks crowded with temporary shelters and shared hearths as dispersed bands compressed into a few safer pockets. Migration, too, would have been part of the repertoire. Not a sudden exodus in a single direction, but a series of nudges. A band that once centered its movements on a particular drowned valley might, over a few years, shift its range 50 or 100 kilometers along the coast. Another might start using a different crossing point, between what would become Britain and the continent, favoring a slightly higher, narrower strait over a now unreliable low route. Some may have moved onto what were, at the time, newly insular high spots, future islands forming from fragments of the Doggerland uplands. And for a while, these might have been productive refuges surrounded by tidal flats and rich fishing grounds. The archaeological record cannot show you those decisions in real time. It only hints. A scatter of tools on a now submerged terrace here, a cluster of later sites on a former headland there. Patterns that suggest some groups were displaced, others learned to exploit the changing margins. For Mesolithic people, coastlines were opportunities as much as threats. As the sea advanced, it brought new resources within reach. Shellfish beds established themselves along rocky fringes and muddy estuaries. Oysters, mussels, cockles. Fish moved in predictable rhythms, congregating in channels, entering lagoons with the tide. Seals basked on sandbanks. Seabirds nested on cliffs and islands. If you could survive the initial trauma, a newly broken coast could become, within a generation, part of a rich subsistence strategy. There is scattered evidence for this adaptation. Along later Mesolithic shores of Britain and northwest Europe, archaeologists find dense middens, piles of shells, fish bones, and burned stones accumulated over many seasons. They find the stakes and alignments of ancient fish weirs, fences of wood driven into tidal channels to corral fish as the water ebbed, sometimes visible today only as dark stains or preserved fragments in waterlogged sediments. They find harpoon points and barbed antler tips, well suited to spearing fish, seal, or large waterfowl. In the woods behind those coasts, life continued in more familiar patterns. People hunted red deer, aurochs, wild boar, gathered hazelnuts, berries, and edible greens, carved dugout canoes from massive tree trunks. The woodland and the water were not separate spheres but overlapping zones. By favoring slightly higher camp locations after the tsunami, groups could keep easy access to both. One path down to the tidal flats and skerries, another into the quiet shade of the forest. The difficulty for us is that almost everything that mattered most in this adaptation was made of things that rot: wood, fiber, hide, plant foods, even the structure of shelters themselves. On a dry, stable landscape, some of that might occasionally survive in anaerobic pockets, deep pits, waterlogged hollows. Around the North Sea, so much of the action took place on ground that is now underwater, subject first to submergence, then to millennia of tidal scouring. Entire landscapes of campsites, fish traps, and boat landings may simply have been erased or buried beyond easy reach. What we do find from this period tends to be the hard, durable residues: flint tools and waste flakes, sometimes animal bone where conditions allow, charcoal from hearths, odd patches of preserved wood where peat or fine sediment locked out oxygen. On submerged paleo landscapes, sonar and core samples occasionally pick up hints of human activity. Concentrations of flint, isolated worked timbers, but our coverage is sparse. Much of the North Sea floor has never been systematically surveyed with archaeology in mind. When a trawler net hauls up a split worked bone point, or a dredger recovers a patch of peat with traces of burning, these are glimpses, not a full picture. That sparseness is why we must be careful. It would be tempting to tell a clean story. The wave comes, Doggerland is shattered, everyone flees to Britain and the continental uplands, and a new way of life begins, organized around narrower straits and sharper coasts. The evidence does not allow that kind of certainty. It points instead to a mosaic of outcomes. Some low-lying territories were probably abandoned earlier than they might otherwise have been. Some bands may have suffered losses they never fully recovered from, their names and lineages ending in the silence of a flooded valley. Others, positioned just a little differently on the map, had a rough season or two, and then found new equilibrium, integrating new shellfish beds, new inlets, new sandbars into the same flexible seasonal routines that had always guided them. Some part of the wave, though, likely survived in memory. In a world without writing, stories are the archive. Mesolithic people almost certainly had rich oral traditions, myths explaining how animals came to be, accounts of ancestors' journeys, rules encoded in stories about what happens if you fish in the wrong place, cut wood from the wrong grove, break a taboo at the wrong time. A sudden, deadly flood that tore through familiar ground would have been an obvious candidate for story-making. Trauma does not have to be relayed as a dated event. On this year, in this month, the sea came to live on. It can shift into a more timeless register. There was once a time when the water rose without warning. There was once a land where our people lived, now lost beneath the waves. The sea can be kind, but sometimes it comes to take what belongs to it. Over generations, specific details blur. The name of a vanished river is forgotten, but the warning remains. Do not trust the low places too much. Build your camp where you can still see the trees behind you. Later flood myths from Europe and beyond are often separated from the Storegga event by thousands of years and complex cultural histories. It would be irresponsible to draw a straight line from any one of them back to this particular wave, but the mechanism, traumatic events entering a culture's oral repertoire, being retold and reshaped as cautionary tales or cosmological anchors, is universal. It is entirely plausible that, for a while, among the Mesolithic bands on those changing shores, people told stories about the day the sea came higher than it ever had before. They did all this without leaving us inscriptions or monuments, only those scattered tools, bones, and sand layers. From that minimal physical record, the strongest signal is not collapse but resilience, a capacity to adjust quickly to new coastlines and food sources, to reweave social ties after disruption, to fold even catastrophe into a longer story of living with water. As the centuries passed, the long trend continued. Sea level kept rising, channels deepened and widened. What had been flooded marsh became permanent estuary. What had been intermittent crossings became deep, swirling straits. The memory of a single great wave may have faded into the broader experience of an encroaching sea. When we follow that story forward, toward the final separation of Britain from the continent, we move from a drowned plain with scattered survivors to a world beginning to recognize that what lay between these lands was no longer just low country, but something else entirely. A sea that could, at last, stand as a boundary. By the time those boundaries began to feel real to the people living beside them, the drama that made them possible had been unfolding for thousands of years. If you roll the clock further back, long before the Storegga Slide, long before the Mesolithic bands we've been following, there was no English Channel at all. Britain was not a neat island waiting to be outlined on a map. It was simply the northwestern corner of a larger peninsula, sticking out from Eurasia into a colder, windier world. During the last ice age, so much water was locked up in vast ice sheets that global sea levels were more than 100 meters lower than today. The North Sea basin was mostly dry land. The Channel was a low river-cut valley. Huge rivers, ancestors of the Thames, the Rhine, the Seine, flowed together, winding through a broad plain before spilling out into the Atlantic somewhere beyond what is now the edge of the continental shelf. As the climate warmed after the last glacial maximum, those rivers changed. The ice sheets retreated. Meltwater surged south. In places where the ground was already low and weak, enormous glacial lakes formed, dammed behind ridges of ice and rock. At some point, probably in a series of episodes rather than a single neat moment, those dams failed. Catastrophic outburst floods roared through the chalk and sediment that now separates Britain from France, carving deep channels, scouring bedrock, gouging what geologists call the Channel River system. These were not tsunamis in the sense of a single towering wave generated by an earthquake or a submarine landslide. They were colossal freshwater floods, sustained torrents lasting hours or days, churning with ice and rock. But they did some of the same work. They weakened the land, cut through saddles and low divides, gave the rising sea future pathways to follow. Then, as the ice continued to melt, sea level rose. Slowly, relentlessly, centimeter by centimeter, year by year. The dry valley of the Channel began to flood from the west as Atlantic water pushed in, and from the east as the low North Sea basin deepened. Low ground was first to go. Marshes, braided river flats, shallow lakes. What had been a continuous landmass became a landscape of bottlenecks and corridors. A little higher here, a little lower there. That was often the difference between a dry crossing and a shallow sound. Doggerland sat within this changing web like a vast, sinking bridge. For a long time it remained a passable, habitable plain. Even as water crept in from all sides, the highest ridges and plateaus stayed dry, connecting what we now call Britain to the continent. But the connections were no longer broad, effortless strolls across open grassland. They were narrowing belts, constricting routes along which people, animals, and ideas moved. This is where the long goodbye begins. If you imagine living through it, it doesn't feel like a decisive break. It feels like a series of adjustments. The old ford is too deep this spring. You use a different one. A once reliable valley now floods each winter. You shift your camp to the flanks of a nearby hill. A crossing that elders remember taking on foot now requires a dugout canoe. People still move, still visit relatives across the water, but the meaning of a cross is changing. By about 8,500 years ago, the English Channel as a recognizable seaway already existed in some form. Most researchers think that by then, southern Britain was effectively, if not absolutely, insular, cut off from the continent by salt water deep enough that normal casual foot traffic was no longer possible. You could cross in a boat, and people almost certainly did, but you could not just walk. In the north, the story lagged behind. Between southern Britain and what is now Denmark, the Doggerland uplands still rose above the water. To the west, what would become the eastern coast of Scotland and England. To the east, the low shores of Jutland and northern Germany. Between them, an increasingly broken set of ridges, bars and shallows that might, at certain tides or seasons, have joined into tenuous causeways. These were the last threads. Sea level rise was already thinning them. Each century, a little more ground vanished. Each storm season, a little more erosion worked at the margins. Even without the Storegga Slide, sometime in the millennia after the last glacial maximum, those threads were going to snap. The physics is inescapable. Add water to the oceans and lowland drowns. So did one single wave create Britain? Probably not in the strict mechanistic way that phrase suggests. The island we know was the end result of multiple processes at different timescales. Slow thermal expansion and melting ice, sudden flood pulses through the channel, countless storms chewing at cliffs and shorelines. The Storegga tsunami was one of those processes, but it arrived in a landscape already undermined, already on the brink of fragmentation. What it could do, and what it likely did, was accelerate local changes that were poised to happen anyway. Picture a shallow corridor, a broad tidal flat only a meter or two above average high tide, used as a crossing in dry seasons, backed by peat bogs and low woodland. The sea has been working on it for centuries. Channels are incising, pools are forming, but at low water adults can still pick their way across, maybe carrying children, maybe pushing a canoe loaded with goods. Into that setting, send a wall of water several meters high. The physics we talked about earlier still applies. When a tsunami rushes over a low plain, its energy is spent not just in depth, but in distance. It pushes inland, slows, and then draws back with immense force, taking everything loose with it. Soil, peat, the thin skin of plant roots that were holding the edge together, they're all vulnerable. In such places, the Storegga wave could have done more than drown people. It could have stripped away stabilizing vegetation, ripped open new channels, deepened shallow swales into permanent inlets. It could have turned a marginal, seasonally passable corridor into a lace network of saltwater tongues and sandbars that, even once the sea calmed, never quite closed again. Multiple. The tsunami, arriving when sea level was already high and still rising, would have nudged the system forward. A crossing that might have remained usable, just barely, for another few centuries might have become untrustworthy or impossible, after a single day of catastrophic retreat and re-inundation. From the perspective of the people living there, the distinction between caused and hastened is mostly academic. If your grandparent could once in their youth walk to the far side of a broad marsh, and you now face a deep, shifting channel where that path used to be, your world has changed. If the place your kin always camped at the narrowest part of the crossing is now a shoal that vanishes at high tide, your world has changed. Whether that transformation took 20 years or 200, whether one giant wave did most of the cutting or just the last part, the practical outcome is the same. The line between over there and over here has thickened. This is the nuance behind the headline claim. To say that a single wave created Britain is a poetic shorthand. It captures something emotionally true, the idea of suddenness, of a night when the sea rewrites the map. But it risks flattening a long, complicated story into a single dramatic moment. Geologically, Britain's island status is the consequence of prolonged sea level rise and repeated erosive events, with Storegga as one powerful chapter among several. Humanly, the separation was experienced not as an instantaneous creation, but as a drawn-out reorientation toward water. Because as the gaps widened, journeys changed. Where once you might have walked to visit allies, now you needed a boat, more planning, better weather. A trip that had been part of a seasonal route became a special undertaking. That shift alone can rewire societies. Boats require maintenance, timber, pitch, skilled labor. They can carry more goods than a person on foot, but they are more vulnerable to storms, to mechanical failure, to currents that don't care about your kin obligations. In some areas, exchange networks probably tightened, focusing more on nearby groups on the same side of the new water. In others, crossings may have become more centralized, funneled through a few families who controlled the knowledge and resources for seafaring. That kind of bottleneck can create power. The people who know when it's safe to cross, who own the best canoes, who know the landmarks in open water and the hidden sandbanks, become indispensable. Over generations, these invisible lines, who you marry, who you trade with, who you can visit in bad weather, start to map onto the visible ones, where the sea lies, how far it stretches, how rough it becomes in different seasons. Geography seeps into identity. People on the western uplands, looking out over a widening channel, may have begun to think of themselves as belonging to this side, these woods, these rivers. People on the opposite shore in what is now northern France or Belgium would have been doing something similar, their own sense of us shaped by subtly different coastlines and horizons. Around the shrinking margins of Doggerland, groups who still remembered older pathways would, with each passing generation, feel the pull of those memories against the facts of the water. Eventually, the stories catch up. There was once a time, someone might say, when our people could walk across there. There was once a land where we hunted deer, where now the seals lie. There was once a place where the ancestors lived that the sea has taken. These are not just laments. They are boundary markers, verbal fences around a shrinking section of home. By the time Britain was unquestionably an island in every practical sense, no more casual crossings on foot, only deliberate voyages by water. The processes that had made it so were already old news to the rocks and the tides. But to the people inhabiting its shores, and the shores facing it, the consequences were still unfolding. Travel was harder in some directions, easier in others. Exchange shifted from broad, flat plains to narrower, salt-edge corridors. The sea that had always been a source of food and danger became, more and more, a line you had to cross with intention. That is the Britain Storegga helped bring into being. Not conjured in a single night, but coaxed into sharper outline by one violent surge in a long rising tide. An island made not just of chalk and clay, but of altered roots, truncated relationships, and a slow, dawning realization that what lay between its shores and the continent was no longer a wet, inconvenient lowland, but something larger, deeper, and, in a new way, apart. To understand how we know any of this, how we can trace an ancient wave's role in such a drawn-out transformation, we have to turn from story back to evidence, to the quiet, layered testimony of sand and peat, shells and silt, and buried landscapes glimpsed through cores and sonar. If you drain away the sea and strip back the grass and heather, what you're left with is layers of mud and sand and rotted plants, layers of shells and pollen and microscopic skeletons of things too small for anyone in Mesolithic Britain to have imagined. Each layer is a moment, a season, a storm, a quiet decade. Stack enough of them together, and you get a record of change that runs far deeper than any human memory. This is where the Storegga tsunami is hiding. Not in a single dramatic scar in the landscape, but in thin, sometimes almost delicate sheets of strange sand, caught between peats and silts in places that, on the day of the wave, were low, wet, and very unlucky. To find those sheets, scientists go hunting in the quietest, softest parts of the coast. Not on exposed cliffs, where the story has been chewed to pieces by every storm since, but in sheltered basins, back barrier marshes, tidal inlets that silted up and turned to bog, inland hollows that collected peat for thousands of years. Places that spend their lives gently accumulating. They walk out over reed beds and heather moors and flat, squelching salt marsh. Then they stop, brace a metal tube against the ground and begin to push. Coring, they call it. A simple idea. Drive a hollow cylinder down into the earth, twist and pull up a plug of sediment. A vertical slice through time. Do this again and again, meter after meter in different spots along a transect from the present shoreline inland, and slowly a pattern appears. When those cores are split open in the lad, the history of the place is laid out in cross-section. Dark, fibrous peat where mosses and sedges built a waterlogged carpet over centuries. Finer grey or brown silts where quiet water settled out suspended mud. Occasional thin bands of charcoal from long-ago fires. Pollen grains that, under a microscope, sketch the rise and fall of woodland and open ground. And sometimes, in the middle of that peaceful, peaty sequence, something abrupt. A pale band of clean, sharp sand, coarser than the mud above and below, sharp-based, cutting into the underlying peat as if it arrived forcefully, scouring and gouging before settling. Sometimes only a few centimeters thick, sometimes tens of centimeters, sometimes pinching out and disappearing a few meters further inland, sometimes persisting. That is the first hint of a tsunami, sand where no normal beach or dune should be, sitting unexpectedly far inland, trapped between layers that whisper of slow, quiet accumulation. Look closer, and the signature becomes more specific. Mixed into that sand are tiny shells and fragments of marine organisms, things that live out in the brackish shallows or offshore, not in rain-fed bogs. There are marine microfossils called foraminifera, with their delicate calcite shells, and diatoms that belong to saltwater, not freshwater pools. In places there are rip-up clasts, torn chunks of the older peat and mud beneath, ripped loose and rolled into the deposit, like pages torn from the book and stuffed back in out of order. Seen under a microscope, the grains themselves tell a story. They are often better sorted and more rounded than storm-thrown debris, more like material reworked from offshore sands and pushed inland in a single, enormous surge. String these clues together. A sand sheet sitting between peats in a low basin, containing marine microfossils, showing signs of violent emplacement, and you have what geologists call a tsunami deposit. But the story is never that simple. The Earth rarely hands over confessions. It gives hints, probabilities, patterns that might match one thing or another. So each candidate layer is interrogated carefully. Could a severe storm have done this? A once-in-a-century surge, perhaps, driving waves over a coastal barrier and dumping sand far inland. Storms do leave overwash deposits, and along modern coasts their signatures provide a useful comparison. Storm layers tend to be patchier, more closely tied to present or former shorelines, their sand less uniform, their inland reach more limited. Tsunami deposits can claw their way much further up valleys and over low divides, ignoring normal floodplains and marching inland along paths of least resistance. So scientists look at distance from the ancient shoreline, at elevation, at the geometry of the deposit. They map how thick the sand is, how far it extends, and how it thins. They compare multiple cores from the same basin, and then from adjacent basins, and then from another estuary tens or hundreds of kilometers away. In Scotland, in the Shetlands, along the coasts of Norway and Denmark, this detective work has revealed sand sheets at roughly the same relative position in the sequence, a sudden marine pulse interrupting the quiet growth of peat and lagoon mud, around 8,200 years ago. To turn around 8,200 years into something more precise, you need dates. Dating mud and sand is not like reading a calendar. It's more like tracing fate pencil marks through a palimpsest. The main tool is radiocarbon, measuring the decay of radioactive carbon-14 in once living material to estimate how long it's been since death. In these cores, that usually means bits of plant, leaves, twigs, seeds, or the organic matter that makes up the peat itself. Scientists take samples just below the sand layer and just above it, and sometimes from within it if there are shredded plant fragments. They send them off to radiocarbon labs, which return ages in ranges, not a specific year, but a span of decades, or sometimes centuries, within which the true age likely falls. Even that isn't straightforward. Marine organisms can appear artificially old because the ocean's carbon reservoir lags behind the atmosphere. This is the reservoir effect. If a bit of seaweed or shell gets mixed into the deposit, its radiocarbon age might mislead. Disturbed layers, where burrowing animals, roots, or later flooding have jumbled the sequence, can also confuse things, moving older material upward or younger material downward. So dates are cross-checked. Multiple samples are taken from closely spaced levels. Outliers, ages that don't fit the stratigraphic order, are flagged and sometimes discarded if there's a good reason to suspect contamination. Calibration curves, built from tree rings and other records, convert raw radiocarbon years into calendar years, adding another layer of probability. When this careful work is done across many sites, a pattern emerges. The anomalous sand sheets in Scottish and Norwegian basins consistently fall in the window of roughly 8,200 years ago, within the uncertainties of radiocarbon, close enough in time to plausibly represent a single regional event. But plausibly is not the same as certainly, and geology rarely deals in certainties. To test the tsunami interpretation further, researchers turn to another tool: models. Numerical models take what we think we know about the Storegga Slide, its approximate size, depth, and shape on the Norwegian margin, and use the physics of water waves to simulate what kind of tsunami it would generate. They propagate that wave across digital reconstructions of the ancient seafloor and coastline, accounting for the lower sea levels of the time, the different shapes of bays and inlets, the presence of Doggerland's still emergent uplands. These simulations spit out maps, how high the wave might have been in various places, how far inland it might have reached, how many pulses might have arrived as the seafloor oscillated and the wave reflected off distant shoals. Then those modeled patterns are compared to the actual deposits. If the model says a 3 to 5 meter wave should have penetrated up a particular estuary and flooded basins up to 10 meters above contemporary sea level, and the highest tsunami sand sheet in those basins is found at roughly that elevation, that's a good sign. If the model predicts little or no inundation in a sheltered corner, and no sand sheet is found there, that absence becomes its own quiet confirmation. Where model and sediment disagree, it's a prompt to rethink both. Perhaps the slide was larger or smaller than assumed. Perhaps local topography has been misreconstructed. Perhaps in that particular basin, what was taken for a tsunami layer really is an extreme storm overwash, or a shift in a river channel, or something else entirely. This is where the debates live, in the messy overlaps between possibilities. Some researchers point to grain-size distributions or sedimentary structures they feel are more characteristic of storm action than tsunamis. Others note the broad regional synchronicity of the deposits and their inland reach, which suggests something rarer and more powerful than weather. In a few locations, what was once confidently labeled a Storegga tsunami layer has, after more detailed work, been reinterpreted. Elsewhere, new cores have strengthened the case. The picture that emerges is not of unanimous agreement, but of converging lines of evidence. A gigantic submarine slide off Norway whose age matches the deposits. A widespread layer of marine sand intruding into inland peats across the North Atlantic margins at about the same time. Grain-scale features, microfossils, and rip-up clasts pointing to rapid, energetic inundation. Models that, while imperfect, show that a slide of Storegga's size could indeed send waves into those very estuaries, to those very elevations. From all of this, scientists build their conclusions, but they do so with a kind of disciplined humility. They will say that a tsunami associated with the Storegga Slide almost certainly struck the coasts around the North Sea about 8,200 years ago. They will say that the sand sheets are best explained by that event. They will estimate run-up heights, inundation distances, and likely low-lying corridors that were scoured or drowned. But they will also keep a margin of doubt. They acknowledge that radiocarbon ranges overlap, that reservoir effects can blur the exact timing. They note that not every anomalous sand layer in every core is securely tied to Storegga, and that some may record older or younger, more local events. They admit that our reconstructions of ancient coastlines and water depths carry their own uncertainties, so modeled wave heights come with error bars. In that sense, the reconstruction of this 8,200-year-old disaster is itself like the landscape it describes, made of firm ground and soft edges, of solid ridges of evidence connected by marshy spans of inference and probability. Yet even with all those caveats, the broad outline is compelling. A slide in the deep, a series of waves hammering into a coast already made fragile by rising seas. sand torn from offshore bars and driven into inland basins, pinned forever between peaks that remember calmer times before and after. In those quiet cores, in the faint glow of lab lights, the night the sea rewrote the map is still there, reduced to a few centimeters of sediment but no less real. From this kind of evidence, we can begin to ask questions not just about water and land, but about people. What did it mean to have your marsh suddenly salted, your crossing turned to a channel, your familiar lowland stripped to bare sand? How might such an event echo in stories, in taboos, in the way later generations talked about the sea's hunger for land? To trace those echoes, we have to step from geology into memory, and from memory into myth. Human memory is short. Human stories are not. If you live in a small foraging band, you might personally remember 30, 40, maybe 50 years of weather and water. Your parents and elders might carry another 30 or 40 beyond that, in fading recollections of when the bog was wetter, or before the salt came in. But stories, if they matter enough, can stretch far further than that. They can cross the gap between lifetimes. Now imagine that you grew up in a place where the sea had, within the last few generations, done something no one alive had ever seen before. Maybe you were a child when the wave came. Maybe you only heard about it. The details would blur quickly. The exact year, the exact height, the exact shape of the coastline before and after, those would dissolve. What might remain are simpler impressions. The place where people used to camp that is now always wet. The path that is now a channel. The old trees out beyond the waves, visible only at the very lowest tides, their stumps like dark teeth in the surf. You might not talk about Storegga or tsunamis or continental shelves. You would talk about a night, or a storm, or a time when the sea came further than it ought. If that meant deaths, disappearances, abrupt uprootings, then the story might be sharpened by grief. It would become something you told children when they strayed too close to the edge. Not because you were trying to preserve an accurate geological record, but because you were trying to keep them alive. Do not build too low. Do not sleep where the old people died. The sea remembers the way in. This is how events become taboos, and taboos become myths. The idea that flood stories might carry traces of real, ancient drownings is an attractive one. It lends our oldest tales a kind of extra weight, a secret double life as history in disguise. And across the world, in many coastal cultures, there are recurring themes that look uncannily like memories of rising water. There are stories of cities that sank in a single night, stories of green fields and forests now lying under the waves, stories of people who angered the sea, or the gods of the sea, and were punished with sudden inundation. In northwestern Europe, long after Doggerland vanished beneath the waves, later peoples began to tell their own versions of sunken lands. Off the coasts of Wales and Cornwall, there are medieval and early modern tales of fertile lowlands now drowned. Kentra Gwaelod, the Lowland Hundred, supposedly lost when a negligent gatekeeper failed to close the sea gates. Lyonesse, a fabled land between Cornwall and the Isles of Scilly, said to have harbored churches whose bells can still be heard beneath the waves on quiet nights. Around the southern North Sea, later Dutch and German traditions speak of lands claimed by catastrophic floods, of churches swallowed, of farms erased. In Brittany there is Keres, the wicked city overwhelmed by the ocean. In Scandinavian sagas and legends there are shifting shores, vanished farms, coasts that creep and bite. None of these stories mention Doggerland. None describe a single wave 8,200 years ago. Their written forms are thousands of years younger than the Storegga Slide, layered over by later storm surges, medieval sea walls, and very human moral lessons about pride and negligence. And yet the pattern, the fascination with land beneath the sea, feels familiar. Part of this is simply geography. Wherever human beings live by coasts, they notice that shorelines move. In estuaries and deltas, the land may advance and retreat over the course of a single lifetime. Storms chew away dunes, rivers build sandbars, headlands slump into the surf. A century of erosion can turn farmland into salt marsh, and another century of sedimentation can turn that marsh into dry meadow again. In low-lying countries like the Netherlands, the struggle between sea and polder has been obvious for as long as anyone has been there to watch. You do not need a once-in-10,000 years tsunami to gain a sense that the sea is hungry. What makes the early Holocene special, though, is the speed of the baseline change underneath all the local fluctuations. From around 11,700 years ago through to the time of Storegga and beyond, Global sea levels were rising rapidly as the last great ice sheets melted. In some places around the North Sea, shorelines were retreating inland by tens of meters a year. A person could see, over the span of their life, the sea permanently claiming places that had once been dry. If you grew up on Doggerland's western flats, you might have heard your elders talk about hunting grounds out there, beyond the low grey line of the horizon, where there were once reindeer or aurochs, or good stands of hazel. For you, those grounds would already be gone. Within a few generations, the maps in people's heads would need constant updating. Crossings that were once simple, low-tide walks would become risky wades, then boat passages, then open water. Islands would form and fragment. What had been a broad plain would turn, piece by piece, into a broken archipelago. That creeping, relentless drowning was a much bigger factor in Doggerland's story than any single wave. The Storegga tsunami was spectacular, but it rode on top of a long rising tide of meltwater. The plain it attacked was already under pressure, already shrinking. The people who lived there had, for centuries or longer, been adapting to a world where water was gaining on them. Still, a sudden disaster has a different emotional flavor than a slow loss. The regular march of high tides inching a little further each year might be noticed with resigned shrugs. A single terrifying surge that blitzes inland, scours campsites, strands fish far from any pool that would demand an explanation. Human beings are very good at explaining things with stories. Maybe your people say that a giant under the sea rolled over in his sleep and sloshed the water. Maybe they say that someone offended the spirits of a river, and the river called the ocean in as an ally. Maybe they say nothing at all, and simply avoid the lowest ground from then on, their silence and caution becoming its own kind of memory. Over hundreds of years, the literal details would fade. There would be no dates, no named submarine canyon, no notion that this wave came from the far Norwegian margin. There would only be impressions, a sense that the sea once jumped, a warning that it could, in theory, do so again. From our perspective, thousands of years later, it is tempting to go hunting through myths for that moment. To hear the story of a drowned realm and say, "Ah, that must be Doggerland." To read of a great deluge and wonder, "Was that the Storegga wave?" But this is where responsible speculation has to slow itself down. There are several problems. First, myth is not a tape recording. By the time a story reaches written form, in a medieval chronicle, a 19th century folklore collection, a modern retelling, it has already passed through countless minds, each adding, trimming, reinterpreting. Moral lessons are glued on. Religious imagery is updated. Characters are swapped out. 2 or 3 older stories may be stitched together into one. Second, similar landscapes inspire similar tales. If you live in a delta prone to storm surges, you will likely have flood myths whether or not any ancient tsunami ever reached you. If you build on a sand spit that occasionally overwashes in big storms, you will sooner or later tell stories about that vulnerability. Sunken cities, lost coasts, and wrathful waters are almost universal because the underlying experiences are common. Third, the timescales are mismatched. Most of the flood traditions we can actually date in writing are a few hundred to a few thousand years old at most. The event we're talking about, the Storegga Slide, is over 8,000 years in the past. Could an oral memory persist that long with any continuous specific connection? We simply don't know. Some researchers point to examples of indigenous Australian stories that seem to recall sea level rise events from several thousand years ago, describing now submerged coastal plains and islands. If those connections are real, and there is serious debate about how tight they are, they suggest that oral traditions can, under some conditions, preserve echoes of ancient environmental change far longer than written history has existed. But can is not always do. It is one thing to say that a myth may reflect at some remove a remembered landscape. It is another to pin a given story to a specific date and event. That second leap is where controversy lives. Some archaeologists and folklorists caution strongly against it. They point out that once a dramatic geological event is proposed in a region, there is a tendency to retrofit every local legend to match, to see evidence everywhere for what we already expect to find. So for Doggerland, for Storegga, the careful stance is this. It is reasonable to think that people who lived through rapid sea level rise and occasional catastrophic floods would develop stories about land lost to the sea. It is reasonable to note that many later cultures around the North Sea told tales of sunken lowlands, drowned farms, and coasts that used to be further out. It is not reasonable, on present evidence, to claim that any particular medieval legend is a direct, unbroken memory of the night the Storegga wave came ashore. Doggerland itself has become a kind of modern myth. We reconstruct it scientifically, through seismic surveys, sediment cores, ancient DNA. We map its rivers and hills, its wetlands and dunes as best we can. But in popular imagination, it's also something else. A symbol of a lost homeland. A reminder that what looks like permanent dry land can, within the sweep of deep time, be as temporary as a sandbar. For people today, it can stand in for all the places coastlines have quietly erased. The villages given up to the sea on the east coast of England, the fields lost to storm surges in the Wadden Sea, the salt-bitten ruins on eroding cliffs. For the Mesolithic families who really walked there, it was not a symbol. It was just home. They did not know they lived on what we would later call a continent or a land bridge. They knew the patterns of the tides, the good fishing grounds, the safe crossings. When those patterns changed, slowly or suddenly, they adjusted as best they could. Perhaps they marked the loss in stories. Perhaps they simply moved inland and taught their children to be wary of low ground. Either way, the boundary between land and sea that reshaped their world is still moving. Today, our coasts are again in motion, this time under the influence of human-driven climate change. Sea levels are rising, storms are shifting, deltas and barrier islands are on the move. We have instruments and satellites and numerical models to track these changes with a precision no Mesolithic forager could have imagined. What we do not have is immunity. In a few hundred or a few thousand years, some of our current shorelines may be as drowned as Doggerland is now. The maps we treat as fixed will look, from that far future, like just one frame in a slow animation of advancing water. People then might tell stories about cities in the sea, roads that now run under the waves, forests that only divers can visit. They might argue over whether those stories remember real places or whether they are only metaphors, somewhere in their libraries or their data archives. The Storegga tsunami will still be there, a spike in a core, a band of sand between peats. Somewhere in their imaginations, Doggerland will still be doing what it does best for us now, reminding us that landscapes change, that the line between myth and memory is often drawn on shifting ground, and that living with the sea has always meant learning and relearning where shore ends and story begins. It would be easy at this point to turn Storegga into a simple warning label. Look what happened once, it could happen again. But the real lesson is quieter, and a little stranger than that. The world those Mesolithic foragers knew is not the world we inhabit now. The shapes of the continents are different. The ice sheets that were still retreating in their time have long since vanished. The crust beneath the North Atlantic has been flexing and rebounding for thousands of years. Scotland is still very slowly rising after being unburdened of ice. Parts of southern England are slowly sinking. Coastlines we see on a modern map are the outcome of that long, restless rearrangement. So we cannot simply lift an event from 8,200 years ago and paste it onto today's risk maps. Doggerland is gone. The undersea slopes off Norway have had 8 millennia to slump, stabilize, and accumulate new sediments. Sea level is higher. Tides are different. Any future wave, if one came, would move through a different maze of banks and basins. And yet, water obeys the same physics. Gravity has not changed. Rock still fails when the forces on it grow too large. A loud lesson from the deep past is still a lesson, even if the stage set has been rearranged. In the modern North Atlantic, the biggest tsunami hazards are not identical to Storegga, but they rhyme with it. There are 3 main kinds of source. The first is the one most people think of, earthquakes. Around the rim of the Atlantic, there are several active fault zones, though none as hyperactive as the Pacific's Ring of Fire. Off Portugal and the Western Mediterranean, the boundary between the African and Eurasian plates creaks and grinds. In 1755, an earthquake near Lisbon, probably on a complex fault system out in the Atlantic, generated a tsunami that devastated parts of Portugal, Spain, and North Africa, and was recorded as far away as the Caribbean. It was not born of a submarine landslide like Storegga, but from a sudden jolt of the seafloor, the classic mechanism. Further north, near Iceland and along the mid-Atlantic ridge, spreading plates can also slip in ways that heave the seabed. Most of these earthquakes are relatively modest and deep, only a subset are the right size and geometry to raise a significant wave. But they remind us that tsunami country is not limited to one ocean. The second source looks more like Storegga itself, underwater landslides. Steep continental slopes where thick piles of sediment accumulate are inherently unstable. You can picture them as vast undersea deltas, built grain by rivers and currents, constantly perched on the edge of failure. Add a trigger, a small earthquake, a gas hydrate deposit thawing, a slope weakened by slow seepage, and a chunk of that pile can let go, accelerating downslope and displacing enormous volumes of water. Off Norway, geologists have catalogued not just the Storegga Slide, but other large submarine failures from different periods. Similar scars dot the margins of Greenland, the Faroe Islands, and the eastern Canadian shelf. Many never produced waves big enough to be noticed by any human eye. Some occurred long before people reached these latitudes at all. But their existence is a reminder that continental margins are not static cliffs. They slump, they fail, they rearrange themselves in pulses and jolts. The third source is more local, but no less important for certain communities. Smaller slides and collapses in fjords and steep coastal inlets. In Norway itself, in Alaska, in western Greenland, there have been recent tragedies where a collapse of rock or sediment into a confined bay has thrown up waves tens of meters high. Disastrous for the settlements on those narrow strips of shore, but barely registering beyond the next headland. These are not global tsunamis. They're fiercely local punches. From a hazard point of view, though, they matter a great deal to the people who live there. All of these processes, earthquakes, landslides, rockfalls, are natural and have been operating for as long as there have been oceans and continents. What changes over time is where people choose to build. This is where the Storegga story becomes relevant in a way that goes beyond pure geology. When scientists drill cores in Scottish peat bogs and find that thin sheet of sand that does not belong there, they are not just satisfying curiosity, they're expanding the long memory of the coast. A single lifetime's experience tells you about the worst storm you've personally seen, the highest surge that left a watermark on your wall, the year when the dunes bit deepest into the village. A handful of lifetimes, linked by stories, might stretch that memory back a couple of centuries. But sediment can remember far longer storms. Rock can remember much older waves. By piecing together a catalogue of ancient tsunamis, where they hit, how far inland they ran, how high they climbed, researchers can begin to estimate the long tail of coastal risk. Not the storm you get once every decade, or even once every century, but the rare, brutal events that may only happen once in 10,000 years, and yet have outsized consequences when they do. On a practical level, that helps in very modern ways. It feeds into hazard maps, into building codes, into decisions about where to place critical infrastructure. Do you put your power station, your evacuation routes, your low-lying suburbs in places that ancient sediments say have been swept before? Or do you treat those scars in the peat as advice from a deeper past and build a little higher? None of this means living in permanent fear of impossible odds. It means acknowledging that the baseline, the normal on which our sense of safety rests, is not fixed. It has a history, and it has a future. For the Mesolithic families on Doggerland, normal was already something they watched shift within a single lifetime. A crossing that used to be dry at low tide, now always wet. A fishing ground that silts up. A marsh that turns brackish. The Storegga wave was an extreme punctuation mark in that ongoing sentence, but it was still part of the same story. The coast is a moving boundary, not a line carved in stone. For us, normal has been shaped by a few relatively calm centuries, in which sea level, on a human timescale, hardly budged. The maps you grew up with, the idea that this city is inland, and that one is on the coast, can feel like permanent facts about the world. Against that background, talk of rising seas and shifting storm tracks can sound abstract, like a problem for someone else in a hazy future. Storegga reminds us how wrong that sense of permanence can be. It shows, in one sharp episode, how a familiar shoreline can be rewritten in a single day or night. It does not say that this will happen to us in precisely the same way, but it does whisper that here and not here, land and sea, are less stable categories than we might like. Now add our own ingredient, human-driven climate change. Global temperatures are rising. Ice sheets in Greenland and Antarctica are losing mass. The oceans are expanding as they warm. Over the coming centuries, sea levels are expected to rise by amounts that, while small on a planet-wide scale, will matter deeply to deltas, barrier islands, and low coastal plains. In some places, the retreat of shorelines could begin to approach, in speed, if not in absolute scale, the early Holocene drownings that ate away at Doggerland. This does not mean a single wave will suddenly create a new Britain. It means that, piece by piece, our own Doggerlands, today's tidal flats, salt marshes, reclaimed polders, and low-lying suburbs, may edge toward the sea again. Not in mythic time, but within the spans of a few generations. Looking backward to Storegga, we gain both perspective and humility. Perspective, because we can see that coasts have always moved, that people have always had to adapt, retreat, reimagine where home could be. Humility, because our technologies, for all their power, do not grant us exemption from that basic pattern. A seawall can buy time, a satellite can give warning. But neither can turn the ocean into something static. For coastal planners, engineers, and communities, the message hidden in those ancient sands is simple: build with memory. Assume that the quiet decades are not the whole story. Leave room for water where water has gone before. Treat very rare events not as fantastical outliers, but as part of the long rhythm of the shore. For individuals lying awake at night listening to this, the message can be gentler. The disasters of the deep past did not end human life around the North Sea. They changed routes, patterns, and shorelines. People shifted, learned, found new ways to live along new edges. The world after the wave was not the same, but it was still a world in which children played, fires burned, and stories were told. If you could stand now out on the shallow banks where Doggerland's rivers once braided toward the horizon, you would feel none of that drama. You would not see the flash of the Storegga surge. You would see only the slow, tidal breathing of the North Sea. Water thick with plankton, sand ripples marching along the bottom, currents curling around the ghosts of buried dunes. Twice a day, the tide would flow over places where red deer once grazed, where hazelnuts were cracked beside small, smoky hearths. Twice a day, it would slide back, leaving only the muted shapes of waves on the surface. The meadows are gone, but the rhythm remains. As we turn toward the end of this story, you can imagine that tide working in darkness, patient and indifferent, over the lost plains and salt-scum cliffs alike. The sea has always been doing this, advancing, retreating, feeling for the edges of the land. Storegga was one loud moment in that endless work. Most of the time, change comes on the softer beat of waves, the almost inaudible lift and fall of water against shore. So we end up here, at this quieter part of the tale, where the wave has long since broken and the sea has gone back to its slow, patient work. We've walked, in imagination, across a continent that no longer exists. We've stood on Doggerland's low hills, listening to wind and grasses that are now silt and sand beneath the North Sea. We've watched the Norway margin give way in darkness, a slope of ancient mud letting go and tumbling into deep water. We've traced the Storegga wave as it fanned out across the basin, steepening, shoaling, climbing into Scottish bays and over low islands. And we've followed the long retreat, Britain's edges softening and fraying as sea level rose, channels widening, marshes turning brackish, paths becoming crossings, and crossings finally becoming sea. It can be the making of Britain was already underway, a drawn-out separation powered by melting ice sheets and rising global seas. For thousands of years, the channel between what we now call England and what we now call France was deepening. The low shelves between Britain and Scandinavia were drowning step by step. The wave arrived in the middle of that process, not at the beginning or the end. For people living in low valleys and along estuaries, it may have felt like an ending. Familiar trails gone, fishing grounds scoured, camps washed out to sea. For the coastline itself, it was one sharp gesture in a much longer choreography of tides, storms, and slow, relentless flooding. That is the strange balance of this story. On one scale, it's about an extraordinary night, or perhaps a few hours in one grey morning, when water rose far beyond any remembered mark. On another, it's about tens of centuries in which shorelines wandered almost imperceptibly, a few meters here, a few meters there, until whole landscapes slipped beneath the horizon. The sea does both. It whispers and it shouts. It eats away at continents grain by grain, and now and then it takes a bite. As you lie there now, you are living on the downstream end of that same process. The map under your pillow feels fixed, but it is only a frame from a very long film. Somewhere under the North Sea, under the shipping lanes and the wind farms, sleep the old river mouths and hazel thickets of Doggerland. Somewhere under modern estuaries lie older coastlines, older flood marks, older stories. If you'd like, you can let your attention widen for a moment to include the place where you're listening from. Not just the room or the building, but the wider landscape, the hill or plain or river valley that holds you. The nearest shore, whether it's a 5-minute walk away or many hours of driving. All of it part of this slow conversation between land and water. I'm curious where that is for you. If you feel awake enough, you're very welcome to share it. In the comments, you can write where in the world you're listening from and what time it is there right now. A city name, a country, near the sea, far from the sea, whatever feels simple. Over time, those tiny notes become their own kind of map, a quiet Doggerland of listeners scattered across the planet. If this journey through lost plains and ancient waves has kept you company tonight, it does help the channel if you gently tap like, or leave a short comment, or subscribe so you can find your way back for the next story. Those small actions are how these long, sleepy histories reach more night owls and early risers who might need them. And if you'd like to wander further into the deep past, there is a book that gathers more of these prehistoric secrets into one place. It follows vanished worlds, near extinctions and forgotten coasts in the same slow, story-driven way you've just heard. You can find it at sleepytimehistory.com whenever you feel like exploring with your eyes open instead of closed. For now, though, you don't need to go anywhere. You can imagine the North Sea as it is tonight, a dark, wide sheet breathing under the sky. The waves you see on the surface are small things, restless but harmless, sliding over an older landscape that no one can look at directly anymore. Down there, beneath trawlers and ferries, lie the outlines of lakes and marshes, buried hearths, the tracks of animals that have not drawn breath for 8,000 years. Of all of it, the water moves in long, unhurried pulses, tide in, tide out, winter storms, summer calms. Once, long ago, a single great wave rolled through and was gone. What remained was the sea itself, going back to its slow reshaping of the world, touching the same hidden contours again and again. You can let that image settle in your mind. Moonlight, or starlight, or just darkness, resting on a surface that hides an entire lost country. The land is quiet. The water is quiet. The change, when it comes, is mostly too gradual to feel. Somewhere within that stillness, people sleep, as they always have along shifting shores. Fires fade. Stories end in the middle of a sentence. The tide keeps breathing, and the world turns, and the ancient hidden landscape waits under the waves, patient as stone. You can keep drifting with it for as long as you need. The sea's slow work will go on without you watching. All you have to do now is rest.